Welcome back to Lesson 5 in our overview of the course Fundamentals of Operating Systems. This series of lectures is based on the textbook Operating Systems Concepts 10th edition by Abraham Silberschatz, Greg Gagne, and Peter Galvin. I'm very grateful for the resources provided by the authors and the publishers for this series. Thank you to everyone. Let's pick up where we left off. As we have already seen, the computer system must provide secondary storage to back up main memory. Most modern computer systems use hard disk drives and non-volatile medium devices as the principal online storage for both programs and data. Solid-state drives are becoming more and more popular and more common. Most programs are stored on these devices until loaded into memory. The programs then use these devices as both the source and the destination of their processing. So you see, the proper management of secondary storage is of central importance to a computer system, which explains to some extent why those earlier microcomputer operating systems were called DOS. The operating system is responsible for the following activities in connection with secondary storage: mounting and unmounting the drive, managing free space, allocating storage, scheduling the disk, protecting disk partitions. Because secondary storage is used frequently and extensively, it must be used efficiently. The speed of the computer is greatly impacted by the speeds of secondary storage system and the algorithms that manipulate that system, which is one of the reasons that solid-state drives have become so popular, because they're so much faster than the magnetic type. At the same time, there are many uses for storage that is slower and lower in cost and higher in capacity than those hard disk drives and solid-state drives. Backups of disk data, storage of seldom used data, and long-term archival storage are just a couple of examples. Magnetic tape drives and their tapes, and the CDs and the DVDs and the Blu-ray drives and the platters are all typically tertiary storage devices. Tertiary storage is not crucial to system performance, but it must be managed. Some operating system leaves tertiary storage management to application programs. Caching is another important principle of computer systems. Here's how it works. Information is normally kept in some storage system, such as main memory. As it's used, it's copied into faster storage system, the cache, on a temporary basis. When the operating system needs a piece of information, it first checks whether it's in cache. If it is, it uses the information directly from cache. If it is not, it uses the information from the source, putting a copy in cache under the assumption that it will need it again soon. Now, there are also techniques we'll explore for the operating system to verify that the source data has not changed from that which is in the cache. In addition, internal programmable registers provide a high-speed cache for main memory. The programmer or compiler implements the register allocation and register replacement algorithms to decide which information is kept in registers and which is kept in main memory. Other caches are implemented totally in hardware. For instance, most systems have an instruction cache to hold instructions expected to be executed next. Without this cache, the CPU would have to wait several cycles while an instruction was fetched from main memory. In fact, generally when your instruction is loaded into the CPU, it brings the address of the next instruction with it, which is stored in a register until it's needed. For similar reasons, most systems have one or more high-speed data caches in memory hierarchy. These hardware-only caches are outside the control of the operating system. Because caches have a limited size, cache management is very important to system design. Careful selection of the cache size and of a replacement policy can result in greatly increased performance, as you'll see by examining this figure on your screen. The movement of information between levels of storage hierarchy may be either explicit or implicit, depending upon the hardware design and on the controlling operating system software. For instance, data transfer from cache to CPU and registers is usually a hardware function with no operating system intervention. In contrast, transfer of data from disk to memory is usually controlled by the operating system. In a hierarchical storage structure, the same data may appear in different levels of storage system. For example, suppose that an integer that is to be incremented by 1 is in file B, and file B resides on the hard drive. The increment operation proceeds first by issuing an I/O operation to copy the disk block on which the integer resides to main memory. This operation is followed by copying the integer to the cache and to the internal register. As you can see, the copy of the integer appears in several places: on the hard disk, in main memory, in cache, and in a register. Once the increment takes place in the internal register, the value of the integer differs in various storage systems. The value of the integer becomes the same in all locations only after the new value is written from the internal register back to the hard disk. In a computing environment where only one process executes at a time, this arrangement poses no problems, since an access to that integer will always be to the copy at the highest level of the hierarchy. However, in a multitasking environment, where the CPU switches back and forth among various processes, extreme care must be taken to ensure that if several processes wish to access that integer, each of these processes will obtain its most recently updated value. You see how important this operating system is? The situation becomes more complicated in a multiprocessor environment where, in addition to maintaining internal registers, each CPU also contains a local cache. In such an environment, a copy of the integer may exist simultaneously in several caches. Since the various CPUs can all execute in parallel, we have to make sure that an update to the value of the integer in one cache is immediately reflected in all other caches where it resides. This situation is called cache coherency. You'll see it in the next slide. And it's usually a hardware issue which is considered below the operating system level. In a distributed environment, the situation becomes even more complex. In this environment, several copies of the same file can be kept on different computers. Since the various copies may be accessed and updated concurrently, some distributed systems ensure that when an updated copy is in one place, all other copies are brought up to date as soon as possible. There are various ways that they can achieve this. One of the purposes of an operating system is to hide the peculiarities of specific hardware devices from the user. In some operating systems like Unix, the peculiarities of the I/O devices are hidden from the bulk of the operating system itself by an I/O subsystem. Input-output subsystem consists of several components. There's a memory management component that includes buffering and caching and spooling. There's a device interface, and there are drivers for specific hardware devices. Drivers, as you know, are files that keep information about the device on how it operates. Only the device driver knows the peculiarities of the specific device to which it's assigned. We already talked about how interrupt handlers and device handlers are used in construction of efficient input-output subsystems. Later, we discuss how the input-output subsystem interfaces with other system components, manages devices, transfers data, and detects input-output completion. If a computer system has multiple users and allows the concurrent execution of multiple processes, then access to data must be tightly controlled. For that purpose, mechanisms ensure that files, memory segments, CPU, and other resources can be operated on by only those processes that have gained proper authorization from the operating system. For example, memory addressing hardware ensures that a process can only execute within its own memory space. We've talked about that already. A timer ensures that no process can gain control of the CPU without eventually letting it go. Device control registers are not accessible to users, so the integrity of the various peripheral devices is protected. Protection, then, is any mechanism for controlling the access of processes or users to the resources defined by the computer system. This mechanism must provide means to specify the controls to be imposed and to enforce those controls. Protection can improve reliability by detecting errors at the interfaces between subsystems. Early detection of interface errors can often prevent contamination of a healthy subsystem by another subsystem that's malfunctioning. Furthermore, an unprotected resource cannot defend against use by an unauthorized or incompetent user. A protection-oriented system provides a means to distinguish between authorized and unauthorized usage. A system can have adequate protection but still be prone to failure and allow inappropriate access. Consider a user whose authentication information, ID and password, is stolen. Her data could be copied, deleted, even though file and memory protection are all working. It is the job of security to defend the system from external and internal attacks. Such attacks include viruses, worms, denial of service attacks, identity theft, theft of service. Prevention of some of these attacks is considered an operating system function on some machines, while other systems leave it to user policies and other software, like my Norton. Due to the alarming rise of security incidents, operating system security features are a fast-growing area of research and implementation. Protection and security require that the system be able to distinguish among its users. Most operating systems maintain a list of user names and associated user identifiers. In Windows, this is a security ID, SID. These numerical IDs are unique, one per user. When a user logs into the system, the authentication stage determines the appropriate user ID for the user. That user ID is associated with all the user's processes and threads. When an ID needs to be readable by a user, it's translated back to the user's name via the user name list. In some circumstances, we want to distinguish among sets of users rather than individual users. For example, the owner of a file on a Unix system may be allowed to issue all operations on that file, whereas a selected set of users may be allowed only to read the file. However, a user sometimes needs to escalate privileges to gain extra permissions for an activity. In Unix, we used to talk about going up to superuser. The user may need to address a device that is restricted, for example. Operating systems provide various methods to allow privilege escalation. That was a pretty good bit of material in that lesson, so let's take a break here, give you an opportunity to review your notes, take care of any assignments that you may have or homework that you may need to do, and when you're ready, come on back and we will finish our overview of the course in the next lesson.